Now, we have talked about the atoms are the basic building block of an element. Now, it's not necessary that only one type of an atom that makes that element. They can be different type of atoms which are going to form that element. अगर आपके different elements हैं, let's talk about the sodium itself, or let's take the example of hydrogen, right? So here we have the hydrogen. Now, this is one atom of an hydrogen. This is another atom of hydrogen. This is another atom. Why do we call them all the atoms of hydrogen? We call them all the atoms of hydrogen because they all have the atomic number 1. And I told you this is a unique number. ये unique number है, ये इनकी identification है. So if I know the atomic number of any element, let's say if I have an element X, I have an element X, and I say its atomic number is 11 and its atomic mass is 12. I know this atom X is basically my, this is my sodium. Okay. Similarly, I have atom Y, and atom Y has the atomic number 12 and its mass number is 24. So these are special unique number which can suggest, which can tell me that this element is basically my magnesium, right? So these are the atomic number and the atomic masses. They are the identification. Like a person, he has a name, the surname. So there are two identities. One is your original name and another one is your surname. Similarly, that is your identity. Similarly, an element has got an atomic number and atomic mass. Now, atomic mass can be different for the same element's atom. अब atomic number जो होता है वो बहुत यूनिक होता है और वो एक एलिमेंट के सारे एटम्स चाहे सेम हो चाहे डिफरेंट हो उनके सब की दिस इज अ कॉमनैलिटी दैट मींस एटॉमिक नंबर मींस उन सब के अंदर नंबर ऑफ प्रोटॉन जो है वो सेम होगा. So all the atoms which belong to the same element will be having the same proton number, means they are going to have the same atomic number. But the atomic masses can be different. The atomic mass का different होने का मतलब क्या है? The atomic mass is basically the sum of protons and neutrons. So proton is same as we have already said. So what is making the atomic mass different? So basically they're going to have a different neutron number. So when you talk about the hydrogen, so this is one atom, this is another atom, and this is a third atom. So this atom when you talk about this atom, right? When you talk about this atom, this and this, the common is your 1. That is the atomic number is same, but atomic mass is 1, 2, and 3. So proton number is same, that is 1 and 1 and 1, but the neutron number is going to be different. That is the reason the atomic masses are different. Iska atomic mass 2 ho gaya, sum of proton and neutron, iska atomic mass 3 ho gaya, sum of proton and neutron. So अगर इस तरह के एटम्स किसी एलिमेंट के अंदर हैं, एक ही एलिमेंट के मुख्तलिफ एटम्स, उनका एटॉमिक नंबर तो सेम होगा तभी वो उस एलिमेंट के एटम्स कहला रहे हैं. लेकिन अगर उनका मास नंबर डिफरेंट है, वी नेम सच एटम एज आइसोटोप्स. सो आइसोटोप इज अ कॉन्सेप्ट व्हिच वाज गिवन इन ओ लेवल्स. सो आइसोटोप्स आर, द डेफिनेशन सेज in AS level they ask you the definitions, right? So isotopes are basically, they are the atoms, they are the different atoms, right? They are the different atoms of the same element. And what is the difference in these different atoms? They are going to have the different nucleon number or the mass number, but they are going to have the same atomic number. The atomic number or their proton number of proton is going to be same, right? So there are plenty of elements which have different isotope present in them. So this is the example of hydrogen they have mentioned. So hydrogen, we can see the atomic number remains the same. That is because the proton number is same. The atomic mass is different. Why? Because the number of neutrons are different, right? So like hydrogen, we have the isotopes of many more other elements. So hydrogen has got 3 isotopes. Similarly, we have the isotopes of chlorine. Let's once again consider the example of chlorine isotopes only. So we have the 2 isotopes of chlorine here on the screen. This particular, the first isotope has got 17 proton in it, right? And similarly, the second also, because the atomic number remains 17 only, so it also has got 17 proton. Now, because these are atoms, so the number of proton are same as number of electron. So the only difference comes when there are number of neutrons. So in order to find out the number of neutrons, what we will do is we'll subtract from the atomic mass the atomic number. So 35 minus 17, we get the atomic number here as so when you having same number of protons, which are same of electron as well, or we can say that they have the same number of atomic number or the proton number, right? So these are the similarities. Now, because the proton number, the electron number, the atomic number are same, so definitely their valence electrons are going to be same. And because their valence electrons will be same, so their chemical properties are going to be same. Their chemical properties, both these atoms will be showing the same chemical properties, right? Now, coming to the differences. When you move on to the differences, now the differences are they will be having the different, they both have different number of neutron. And because they have the different number of neutron, that means they have different atomic masses. Okay, so atomic masses we also call the nucleon number. So there's a difference between their nucleon number as well. Now, because the masses are different, that's why their physical properties will be different. Their physical properties will be different, and the physical properties for example, the rate of diffusion, the diffusion rate will be different, and the property like the densities are going to be different. So they will be having all the isotopes will be showing the same chemical property, but there will be a variation in their physical property. So number of neutrons will be 18 here, 35. You subtract from 17, you get the 18 neutrons. Similarly, the second isotope will be having 17 subtracted from 37. So you have 20 neutrons here. So the basic difference lie in the number of neutrons. In the first atom, there are 18 neutrons. The second atoms, you have 20. When you see the difference between the two atoms, two different type of atoms, which are still known as atoms of chlorine, which are still known as isotopes of chlorine. So what are going to be the similarities between them, and what are going to be the differences between them? So let's talk about the similarities between them. So when we talk about the similarities, they will be having. So we know what are isotopes, right? So now we need to understand that how were these isotopes detected or identified. Now there is an analytical tool, and that analytical tool is known as mass spectrometer. Now this mass spectrometer actually is a simple device, is a simple tool. It's an analytical tool basically. It's an analytical tool used for analysis of the chemical compounds, right? Now, this particular tool help us to detect the different atoms which an element possess. Now, I'm just going to show you a simple layout, and in that particular mass spectrometer, we actually the element, it undergoes these 5 stages, these 5 processes: the vaporization, ionization, acceleration, deflection, and detection. Now, after this, when this element, the sample of the element, when it undergoes all these 5 processes, so what happens? At the end, the different type of atoms which are present in an element, which are basically the isotopes, are identified, and are identified and they're detected in a computer probe, and you get a graphical representation of that, which is also known as mass spectra. So basically, the mass spectrometer is a device, it's an analytical tool which help us to determine the average atomic masses of an element. Now, how comes we get the average masses? Because we are able to identify the different isotopes which are present, and their percentage abundances as well. So we are able to identify the different type of isotopes and their percentage abundance. So when we have the averages, the percent on the percentage abundance के बेस पे जब आप उनकी isotopes की overall average calculate करते हैं तो आपको उस particular element का atomic mass पता चल जाता है, ठीक है? So I'll just show you the layout of that apparatus, the mass spectrometer, और किस तरह से elements आप जब अंदर एलिमेंट जब आप उसके अंदर सैंपल ऐड करते हो तो किस तरह से डिफ्लेक्शन और डिटेक्शन के बाद आपको आइसोटोप्स मिलते हैं और मास स्पेक्ट्रा किस तरह से आपको मिलता है. I'll just show you, right? And what kind of questions which are related to this particular learning outcomes are given in the CI. We'll be practicing after this, after we study about little bit about the mass spectrometer. So this is a simple layout of the mass spectrometer. Now what happens here, the sample is from this particular end, आपके इस particular end से यहाँ से आप sample को insert करते हैं, ठीक है? You just provide the sample from this particular end. The sample is added from here. Then what happens here? Then the ion source, there are high electron beam जो है वो यहाँ पर सैंपल जो उसमें से पास कर रहे हैं, इलेक्ट्रॉन बीम उसके ऊपर स्ट्राइक करती है, ठीक है? तो ये इलेक्ट्रॉन बीम जब इस सैंपल के ऊपर स्ट्राइक करेगी तो ऑटोमेटिकली जो उसके जो वैलेंस इलेक्ट्रॉन्स होंगे, जो आउटर शेल इलेक्ट्रॉन्स होंगे, दे विल बी स्ट्राइकिंग, दिस इलेक्ट्रॉन बीम विल बी स्ट्राइकिंग दोज इलेक्ट्रॉन्स, जिसकी वजह से आपके यहाँ पर एक पॉजिटिवली चार्ज आयंस फॉर्म हो जाते हैं, ठीक है? वो इलेक्ट्रॉन्स लॉस्ट हो जाते हैं और आपका पॉजिटिवली चार्ज आयन फॉर्म हो जाता है, ठीक है? उस पॉजिटिव आयन, तो दिस प्रोसेस इज नोन एज आयनाइजेशन व्हिच हैपेंस इन द बिगनिंग. After the ionization, the element that exists in its positive ion form, now what happens? It is passed through the electric field, और electric field में इसको जब आप पास करते हैं, this is, तो यहाँ पर क्या होते हैं, ये ions जो होते हैं, they start accelerating, और वो accelerate करके वो एक magnetic field के अंदर enter हो जाते हैं. तो यहाँ magnetic field में जब ये ions pass होंगे तो on the basis of the different type of atoms, the different type of isotopes, they have the different atomic masses. तो उस atomic masses के difference की वजह से यहाँ पर जो आयंस होते हैं, जो पॉजिटिवली चार्ज आयंस होते हैं, वो डिफ्लेक्ट होने लगते हैं, और जो लाइटर आयंस होते हैं वो ज्यादा बेंड हो रहे होते हैं, और जो लेस लाइटर आयंस होते हैं, जो हेवी होते हैं, वो कम बेंड होते हैं, और जो सिर्फ जो आयनाइज ही नहीं होते हैं वो पार्टिकल्स, वो जो है वो दे आर लॉस्ट इन द प्रोसेस. और जो आयंस जो होते हैं और जो जिनका डिफ्लेक्शन होता है, तो यहाँ पर क्या होता है, ये आगे आते हैं, दे आर पास फर्दर, और यहाँ पर आके इनका दे आर बीन डिटेक्टेड बाय सम प्रोब, और ये कंप्यूटर से अटैच होता है, और जहां पर जो डिफरेंट एटम्स हैं उस एलिमेंट के, जिनका डिफरेंट एटॉमिक मासेस है, वो ये डिटेक्टर डिटेक्ट करके और उसकी रिकॉर्डिंग कंप्यूटर पे आ जाता है. तो दिस इज बेसिकली द काइंड ऑफ ग्राफ विच यू गेट, एंड वी कॉल दिस मास स्पेक्ट्रा, ठीक है? ये मास स्पेक्ट्रा कहलाता है. अब हमारा जो टास्क है, जो सीआई का जो लर्निंग आउटकम है, वो इस ग्राफ को रीड करना है और इस ग्राफ से आइडेंटिफाई करना है कि कितने आइसोटोप्स हैं और उनकी परसेंटेज अबंडेंस क्या है, और उन परसेंटेज अबंडेंस के बेसिस पर आपको उसका ये जो एलिमेंट आपने यहाँ जो सैंपल एंटर किया था, इसमें कितने आइसोटोप्स हैं, और इन आइसोटोप्स की परसेंटेज अबंडेंस के बेस पर आप उसका एटॉमिक मास, एवरेज एटॉमिक मास, वो आपको कैलकुलेट करना है. So the whole thing, what we're supposed to know, to read this mass spectra. The rest of the process is not required by our students. As I've shown you in the previous figure, the mass spectrum. So this is the basically known as mass spectrograph, or it is known as mass spectrum, right? So we get a mass spectrum in the form of this representation. On the x-axis, we have the different the atomic masses, which are going to be the atomic masses of different isotopes. Now, the peaks which are being shown in this mass spectra are the different type of isotopes or different type of atom which are present in that sample of an element. So this sample X, let's say this sample X has got how many isotopes? It has got, let's count the number of peaks because these are the different type of atoms which are there. So 1, 2, 3, and 4. So that means the element X has got 4 different type of atoms which are known as isotopes. And these isotopes will be having the same number of proton and the same number of electron. And because they have the different number of neutrons, that's why it's showing the different mass atomic, their mass number is different, right? So we will be reading the mass number, which will be which is actually put up on the x-axis. So on the x-axis, we have the mass number, we have the atomic masses, which are of different four different isotopes, right, of this element X. And on the y-axis, we have the percentage abundance. Now we can see that if we talk about the isotope with the least atomic mass, so its percentage abundance is basically approximately 23%. The next one, which is slightly heavier than this first one, this is the second isotopes, and its percentage abundance, the relative percentage abundance is basically 10. And the third isotope of this element X, or the third type of atom of this element X, has approximately 46%. And similarly, the fourth isotope has got approximately 21%. Now, when we have these percentage abundance and when we have the atomic masses of the different isotopes, we can simply simplify them. We can take out the average on the basis of the percentage abundance, and we can calculate the relative atomic mass of this element X, right? Now, let's suppose the masses of these different isotopes. I'm just making a random, I'm giving them a random number. Let's say the mass of this, the first isotope, let's say it's 24. The next one is basically is going to be 25. This one is 26 and this one is 27. These are basically the atomic masses. These are different atomic masses of the different isotopes of the element X. And we have the percentage abundance, right? Now, on the basis of the percentage abundance and on the basis of the different atomic mass of different isotopes, we can calculate the relative atomic mass of this element X. Now, how we'll do it? Now, what we will be doing is, in order to calculate the masses, we have the percent, so the percentage abundance of the isotope whose atomic mass is 24. So we'll do it. We need to calculate the average. So we'll write down 24. How many times? What is its percentage abundance? It's 23%, right? And then we have the other isotope, which is basically 25, and its percentage abundance is how much? It's just 10%. And then comes the next one, which is 26. Its atomic mass 26, and its percentage abundance is basically 46%. And similarly, we have the fourth isotope, which is basically 27, and its percentage abundance is 21%, right? So its percentage abundance is 21%. And then what we will do next, we will be simplifying this value. On simplification, we got the answer. The relative atomic mass of this element X will be 25.85, right? So what we did, we had the isotopic atomic masses and their percentage abundance. So for the first isotope, then the isotope atomic mass along with its percentage abundance. Then we have the third isotope with its percentage abundance and the fourth isotope with its percentage abundance. And we added all these values together in order to get the relative atomic mass of the element X. So this is 25.85, which will be considered the relative atomic mass of the substance or the element which is X, which has got four different isotopes or four different atoms presented. So this is how we calculate, and this is how we read the mass spectra or the spectrograph, right? Now proceeding with a few more questions related to it. So this is the slide which is actually defining or telling us the whole process. So if we need to calculate the average relative atomic mass of any element, जिसका आपको isotopes की atomic masses और उनकी relative abundance पता है. So what are we going to do is, the step one is a average mass of all the isotope of an element is taken. So we take the average mass of all the isotope along with their percentage abundance, and we read the percentage abundances and the masses of the isotope from the mass spectra. And then what we do is we put them in the formula. So these are the masses of different isotopes, okay? So these are the isotopic masses. And we multiply them by their percentage abundance. So isotope 1, this is the isotope 1, its mass and its abundance. So this is an isotope 2, isotopic mass 2, right? Its mass and its percentage abundance. And then what we do is we take out the average, and that is how we are able to calculate the AR of an element. And this value, which we calculate on the basis of the data given from the spectra, this value is actually the value which is given in the periodic table. In this, let's do another example. They have given us the chlorine and its isotopes, average masses and their abundance. So in order to calculate the average atomic mass or the relative atomic mass of chlorine, their abundances of the different atoms are mentioned here. So chlorine 35, the isotope of a chlorine, its atomic mass is 35 and its abundance is 75.77%. There's another isotope of chlorine, which is chlorine 37, and its percentage abundance is 24.23. Now, in this particular question, they have not given us a mass spectra, but they have quoted the values in the question. So what we will be doing is we will be just writing down the atomic masses of the different isotope. This is the first isotope, its mass, and what we'll be multiplying it with its percentage abundance, right? This is the second isotope along with its percentage abundance, and we will take out the average of this, right? So we will be getting the answer, that's 35.48. So we basically get two type of a question. One, we have to read the spectra and we have to take out the values of different isotope and the percentage abundance. The second type of a question is that all the values are quoted in the question and we just have to put them in the formula and we have to calculate. Okay. Now, this is the third type of question we get in the past papers. We get to see in the past papers what happens here. This is, I'm just reading it out. The gallium has two natural occurring isotope. We have a gallium 69, that's one isotope of gallium, and another one is gallium 71. And with the masses of 68.9257 AMU and 70.9249 AMU respectively. You need to calculate the percentage abundance of these isotopes. So what they have given you here the net AR, the relative atomic mass of the different isotopes, right? They have given you the relative isotopic masses, and they want you to calculate the percentage abundance. And we know that the galliums, actually the AR, we have to take it from the periodic table. That's basically 69.7231. Now, how are we going to do this question? It's simple. So this is the relative atomic mass of the element of the gallium, which we have taken from the periodic table. The first isotope, right? The first isotope's its relative atomic mass is mentioned here. What we have done next is that we have assumed its percentage abundance as X, right? And this is the second isotope. The next isotope we have, this is the second isotope. And we are going to assume its percentage abundance as Y. Basically, what is it? It's basically 100 minus X, right? So we can either say it's Y or we can take it as 100 minus X. When you will be simplifying this value, what we will do is we will multiply this value by 100 and we will make an equation. So because this is being moved on to the side, and then we will find out the value of X. When we'll find out the value of X, the value of X is going to be the gallium 69 and its value is going to be 60.1%. So if gallium 69 is 60.1, so what we'll do is 100 minus 60.1 will get the percentage abundance as 39.9% for gallium 71. So this is how the unknown percentage abundance of the different isotopes can be calculated. So this is the third kind of question which we have seen in the past papers. There's one more category which I've taken the question from the recent past paper. I'll show you the next, which it's on the next slide. Now, this particular question is from the recent year, and it says that, and I'm just reading it out. It says that silicon is found in many compounds in the earth crust. Silicon has the three natural occurring isotopes. There's silicon-28, silicon-29, and the silicon-30. Now, the table shows the data for silicon-28, 29, and 30. The different values are mentioned here. The relative isotopic masses are given. So 28, its mass is 28, 29, its mass is 29, 30, its mass is 30, right? Now, a sample of silicon contained 92.2 silicon-28, and the total percentage, it's the separate percentages of 29 and 30 is not given. They have given us the total percentage of both of these. Okay, both of these is mentioned to us, and that is basically 7.8. That's a sum of silicon 29 and the silicon 30. So they have given us the percentage abundance of both these as 7.8%, right? Because silicon 28 is itself is 92.2%. Now they're asking you the relative atomic mass of the silicon is said to be 28.09. You need to find out the percentage abundance of silicon 30, and you have to have the answers up till 1 decimal place. We have to be very careful with whatever the instruction they have given you. They want it in 2 significant figures or they want it in 1 decimal place. We have to completely abide by that. Now let's see the answer to this question. It's already been solved on the next slide. Now the solution is something like this. We know they have already mentioned the AR for the silicon, which has been taken from the periodic table, and it's already there in the question. It's 28.09. This data is also given to us that 92.2% of 28 exists, right? Now this all has, this is our, because we're talking about the relative percentage abundance. So this is your isotope 1, this is your isotope 2, and this is your isotope 3. So let's ignore this part. This is divided by 100. So this is already given to us as 92.2, and they have said that the isotope 2 and isotope 3, that's their sum of the percentage abundance is actually 7.8. It's basically 7.8, right? So considering that the sum is 7.8, so if the second isotope is basically, let's consider that as an X, right? So we have the X percentage of the second isotope. We'll multiply it by its relative isotopic mass, which is 29. So the next isotopic mass is 30. So that is going to be, you'll multiply by, because the sum of both is 7.8. So the isotopic percentage abundance of the 30 will be 7.8 minus X, right? So when you will be simplifying this, so you will be getting the value of X as 6.6%. So if the value of X is 6.6%, so silicon 30 is going to be 7.8 minus 6.6. So that its percentage is going to be 1.2%. So this is how we will be calculating if the value of 2 are given to you as unknown and the sum of their relative abundance is given. So these are different questions which have been coming in your examination papers, and that's all for today. And inshallah, we'll cover the next subtopic of the atomic structure in the next video. Thank you.